So, before you actually start working on Born Haber cycles, you need to make sure that your definitions are thoroughly learned. So let's just go through the ones that you are probably going to need, and one or two that you may not come across, but they're worth knowing just to note the difference between some definitions. So let's start with the basic one: enthalpy, standard enthalpy of formation, delta H F. Now what I intend to do here is just to go through the equations. You've got to go away and learn the definitions and make sure that you understand them thoroughly. Here, for example, enthalpy of formation of 1 mole of a compound from its elements in their standard states under standard conditions. Make sure that you know it as well as that. So, for example, standard enthalpy of formation of sodium chloride, for example, formation of 1 mole of sodium chloride involves the elements in their standard states. Notice it's not necessarily 1 mole of elements in their standard states, because we only need half a mole of gaseous chlorine for this particular reaction. So you've got to take care with that and make sure that you thoroughly understand that and are able to work with that. Other ones that you've probably come across: ionization energies, delta HIE, I suppose you could write it as standard state like that. Again, the formation of 1 mole of gaseous ions, or the removal of 1 mole of electrons from 1 mole of gaseous atoms. So Na gaseous, notice Na plus gaseous, like that, plus an electron. The mode of removal of the electron is not necessarily indicated in any way. Of course, we also have the possibility of second ionization energies, where we're removing another electron, and of course third and fourth ionization energies are also possible. But that's the second ionization energy of sodium. Now, one that's relatively new, maybe to you, is the opposite of ionization energies, and that's electron affinity. So whereas with ionization energies we are pulling an electron out, electron affinity, on the other hand, is dropping an electron in. 1 mole of electrons into 1 mole of gaseous atoms for first electron affinity. So here we are, here's an electron, and forming O gaseous minus. Now the enthalpy change for this is going to be negative. You tend to find that the first electron affinities for atoms, gaseous atoms, is always exothermic, because we're going to form interactions between the electron that we're adding and the positive nucleus of the oxygen atom. So we're forming interactions there. But of course, once we've actually added that electron to the oxygen atom, we now have a high degree of electron density within the oxygen ion. Now that means that what we have is not only the attractive force between the electron that we're dropping in and the positive nucleus of the oxide ion O-, but we also have the repulsive forces between the electrons within the atom itself and the electron that you are adding. And for that, you tend to find that the repulsive forces between the electrons and the electron being added are greater than the attractive forces between the electron that you are adding and the positively charged nucleus. And that means that this process is an endothermic process. So that's electron affinity. Enthalpy of atomization. Oops. Let's get rid of that and try again. Delta H8 at. There we go. Formation of 1 mole of gaseous atoms from its elements. So we can have, for example, Na solid going to Na gas, like that. Note that we're always forming 1 mole of gaseous atoms, so that the enthalpy of atomization of chlorine involves forming 1 mole of gaseous chlorine atoms, and that of course can only come from half a mole of gaseous chlorine molecules. So you've always got to remember that we are forming these materials like that. Now be aware that you may also come across at some point enthalpy of atomization of molecules. So for example, CH4 gaseous going to carbon gaseous plus 4 hydrogens gaseous. You could also describe it as the enthalpy of atomization of methane. We're going to concentrate pretty much on ionic compounds here, so I'm not really going to be worried about that sort of process. So that's enthalpy of atomization. Now the difficulty with a lot of this is that you tend to find that some definitions can be reframed, or they seem a little bit similar. Let me give you an example of what I'm talking about. So for example, let's see if I can get this to work out. Let's have a look at this equation. H2 plus half O2 going to H2O. Now how would you define that enthalpy change? Now some of you may say, well, that's an enthalpy of formation of water, because you're forming 1 mole of water in its standard state liquid from its elements in their standard states. Alternatively, however, you could describe that, of course, as the enthalpy of combustion of hydrogen, because we're starting with 1 mole of hydrogen and we're completely burning it in oxygen. So we can reframe that definition. So you have to take care with some of these. Now I don't want to save that. And here's an example of that. Bond enthalpies. So for example, if we take the chlorine-chlorine bond enthalpy here, and break a chlorine-chlorine bond, Cl2 gaseous is going to go to 2Cl gaseous. That's that enthalpy change there. And that, of course, you can see is equal to twice the standard enthalpy of atomization of chlorine. So you have to be a little bit careful with some of these definitions. Make sure that you understand what they are and what they mean. Other ones, well, we've got enthalpy of sublimation. Now I'll mention this one, although you may not necessarily come across it too much these days. Enthalpy of sublimation, as the name suggests, it's the conversion of 1 mole of an atom in its 1 mole of a compound in its 1 mole of a substance in its standard state to its gaseous form. So for example, we can talk about solid sodium going to gaseous sodium like that. Now in that case you will certainly note that, I hope, that this equation here, standard enthalpy of sublimation of sodium, is actually exactly the same as the standard enthalpy of atomization of sodium there. So those two are the same, but you have to be a little bit careful with this, because if I were to take, for example, iodine is in the form of a solid, and we talk about the sublimation of that, I'm going to get iodine molecules in their gaseous form. So whereas in the case of sodium we're breaking strong metal bonds, if you like, metallic bonding, in the case of iodine there, we're not breaking that strong covalent bond between the two atoms. What we are doing is just breaking the weak intermolecular forces between the molecules. So you have to take a little bit of care with that. Compare that iodine in terms of sublimation with the enthalpy of atomization of iodine. There we're going from I2 solid going to I gaseous. Note the difference between those. Others that you need to be aware of: enthalpy of vaporization, delta H standard vaporization, a bit like sublimation, in that you're just changing states generally. So for example, you go from a liquid phase, bromine for example, liquid, going to bromine vapor. Notice again that all that you are doing is breaking the weak intermolecular forces between the molecules and not breaking the strong covalent bond between the atoms. Lattice enthalpy, delta H lat. As it suggests, it's about the lattice of an ionic compound. Now it comes in two different forms. You can talk about the formation, lattice enthalpy of formation of a compound, where we're talking about the gaseous ions coming together to form our solid compound. And this will always be negative. An exothermic process, strongly exothermic in that case. But of course, the alternative is the opposite, the lattice enthalpy of dissociation. Now, in this case, we're starting with the solid sodium chloride, for example, and we're going to form gaseous sodium ions and gaseous chloride ions, like that. And in this case, because we're breaking those interactions, those electrostatic interactions, we've got an endothermic process. But of course, in terms of magnitude, the lattice enthalpy of formation and dissociation are essentially the same. It takes as much energy to break 1 mole of sodium chloride lattice into its gaseous ions as is given out on the formation of 1 mole of sodium chloride.